Now we have Shashank, who will be telling us about optimal baseline corrections for off-policy contextual bandits.
Hello everyone, my name is Shashank. I'm a PhD student at the University of Amsterdam, and this is joint work with Olivier, who just presented, and my advisors Harrie and Maarten. All right, let's start. So just what is the agenda? So I'll start with the background, and then I'll talk about off-policy evaluation and learning and some problems with it. Then I'll talk about our proposed method and results. Now some background on contextual bandit. What is a contextual bandit? So contextual bandit is one-step reinforcement learning. So the general idea is you get a context vector from the environment, and then which is feed into the policy. Policy takes an action, and the environment gives a reward R, and then we log that in a buffer. Now this is general view because this is a RecSys conference. So what is a RecSys view? So user visits the platform. Let's say you're running a bandit on a consumer app. So user visits the app. That means user has some features, and then platform recommends an item. That is the action. Then user decides to click or not click or give any other feedback, which is R, and then we log this. So this is the RecSys view. Now what is the objective function? Mathematically, the value of your policy pi is expected reward, where expectation is over all context. So we average over all context, and then given the context X, we also average over all actions, and then just take the average of the reward from the given context and actions. Now there are two flavors of contextual bandit, or two categories. One is on policy and other is off policy. Now on policy deals with an online setting where you deploy the policy, you observe the reward, and then update the policy, everything in real time or with some slight delay. Now off policy is you deploy a policy online, then you record the logs, and then you train or evaluate offline. We're not interacting with the environment in the off-policy setting. Now, a real-world example of a value could be, let's say, you're running an e-commerce service and your reward is clicks, then the value which you're trying to optimize or evaluate on policy or off policy would be click-through rate. Now, what is briefly off-policy evaluation and learning? Now, the on-policy setting deals with deployment of the new policy. Now, the risk with this is if the new policy is bad, then it could lead to negative user experience, bad business metric, and so on. Now, the off-policy deals with can we evaluate or learn a new policy without deploying it. So alternative is we use the samples from the already deployed policy pi naught. Now, how to do off-policy evaluation or learning? We use importance sampling trick. So this is the off-policy estimate, which can be used for learning and evaluation, which involves importance sampling ratio, which is pi over pi naught into R. Now I'll slowly come to our contribution. But first I'll introduce what is the problem with these off-policy or on-policy estimate. So for on-policy learning, this is the form of gradient. The only important part is log policy in this. Now log policy generally has high variance because policy is from 0 to 1. It's generally probability distribution. So its value is between 0 and 1. And log of, if you transform 0 and 1 with log, the range is minus infinity to 0. So there's high variance with, on policy learning. And similarly with off-policy learning, there's 1 by pi naught term. Again, pi naught is between 0 and 1. So if pi naught is very small, this might blow up. So this also has high variance problem. So how can you improve that, or how you can reduce the variance? There's a trick called baseline correction. So the idea is very simple. We add and subtract a baseline term, or also known as control variate. Now why does it help? Now mathematically you can see that if the baseline correction or control variate has a positive correlation with the reward, then the variance of this estimate will be lower. So that means you can have lower variance evaluation and learning. Now what are some existing baseline correction methods? there's doubly robust method where the baseline term is a regression model. And also you can use average reward. All right, now coming to our contribution. So this is our first contribution where we propose a baseline correction term for evaluation. So the problem was the off-policy evaluation suffers from high variance problem. So we formulate, so we just simply try to find a baseline which minimizes the variance. And it turns out very nicely that the optimal baseline has a closed form solution, which is this equation. This looks a bit scary, but this is just weighted average of reward, where weight is importance sampling square minus importance sampling. So this is baseline correction for evaluation. And similarly, we propose a baseline correction for learning. So in learning, we are dealing with gradient, or the problem is variance of the gradient. So we again formulate the problem as, can we find a baseline correction term beta which can minimize the variance of the gradient? And again, it turns out there's a nice closed form solution, which is this. And again, it's a weighted average of reward, where weight in this case is norm of gradient divided by importance sampling square. Now, does it actually work? So our experimental setup is we use the open banded pipeline, which is an open source library from Cornell by Utah Saito. And in our experiments, to simulate a more realistic setup, we vary the number of actions, which in RecSys terms is we vary the number of items. And we also, our logging policy is a softmax policy, so we also vary softmax temperature. And if you're interested in reproducing or trying it out, our code is open source. I have some results. I know there are a lot of figures, but the important part is, so we are these results are MSE, or mean squared error of the estimator. The lower, the better. So the green method is our proposed method, and we compare with popular off-policy estimators like SNPs, doubly robust, and IPS. And you can see under all different settings, our estimator has the lowest mean square error. That means it has lower variance than other estimators. So this is for off-policy evaluation. Now does it work with off-policy learning? Again, so we run experiments on abandoned pipeline. We train a policy offline and then evaluate it in an online fashion. So we are measuring the value of the policy online. So the higher, the better. So again, green one is our method, and this orange one is BanditNet, which also uses a baseline correction, but a constant baseline correction. And blue one is IPS. And under different settings, our method results in highest test policy value. All right, just to summarize, off-policy evaluation learning suffers from high variance problem. Now, can we reduce the variance? So yes, you can. So standard way is to use control variate, also known as baseline correction. So in this paper, we propose a closed form variance-optimal baselines for evaluation and learning, which you can plug in your implementation, and we empirically show that it indeed reduces the variance for both evaluation and learning. That's it. Thank you. If you have any questions, I'll be happy to take.
Okay. Do we have any questions from the audience? We don't have any on Slido, so thank you.
Thank you.
The next speaker is Tatsuhiro